So in this video, we're going to talk about oxidation reduction reactions, or we simply call them redox reactions. Now, redox reactions, basically what happens is that electrons are transferred from one atom to another. All right, so that's kind of the big thing. As a result of an electron's transfer in the redox reaction, the number of electrons assigned to individual atoms in various reactants changes. So as you compare an atom from the reactant side to the product side, we see that the number of electrons change. And the way that we typically see this is by the difference in charges. And so like if we have an atom here as in a reactant, and on the product, we see the atom all of a sudden its sign change. All right, it has a different charge from than what it was in the reactant side, then we know that this atom has gone through a redox reaction. Okay, now there are two parts to a redox reaction. All right, you have the oxidation, and then we have the reduction. Okay, and so let's talk about each of these in a little bit more detail. So oxidation is the loss of electrons. So it's when something is losing some number of amount of electrons. All right, it doesn't really matter the number, but it lost electrons. So for example, if it starts off as a neutral substance, right, and then we notice that it becomes more positive, okay, then that substance has been oxidized. That atom has been oxidized. Okay, and so regardless of whatever the initial charge may be, so like, for example, if it starts off with, like I say, X, it has a -3 charge, and then we notice that it becomes an X -1 charge, then it lost electrons. In this case, it has been oxidized. Okay, now reduction is when a substance or an atom gains electrons. Okay, and so here we have X, right? And if it becomes more negative, then we know that that substance has been has been reduced. Okay, it has undergone reduction. All right, and regardless of however you want to look at it, so if you go from X 3 plus to X plus, well, you notice it gained electrons, so it's been reduced. Or if it's gone from X, let's say negative, to X 4 negative, all right, whatever the case, it gained electrons, so that substance has been reduced. So let's look at an example here. So here's a chemical reaction where you have a copper solid that reacts with a silver in solution, and what's going to happen is then you make a copper ion aqueous and then a silver metal. Okay, and so let's kind of look at the charges, because if you compare the charges from one substance to the next, and you can see what has been oxidized and what has been reduced, right? And so, like, for example, let's look at this copper here in initial. So you have CuS, right? And you see there's no charge here. So this has a charge of 0. There's no charge, right? But now let's compare the copper on the reactant side to the copper on the product side. The copper on the product side has a 2 plus. All right, so you notice the charge has changed. All right, how did it change? Well, it started out with 0 to a 2 plus. That means in this case, it lost 2 electrons. If it lost 2 electrons, then this copper has been oxidized. And I just realized I spelled that wrong. Oxidized. All right. So copper gone through the redox reaction, and it has gone through oxidation in of itself. Okay, now let's look at silver. Let's see what's going on with silver. Silver starts off with a +1 charge. All right, that's its charge. All right, let's look at it in the product side. In the product side, there's no charge here, so this is a 0. All right, and so when we're comparing one to another, what we see here is that silver ends up gaining electrons, right? So it gains electrons, and because there's a 2 here, so 2 silvers 2 electrons. So it gains 2 electrons. In this case, silver has been reduced. All right, and so this simply means that silver has gone through reduction. All right, now a couple of things that I want you to be aware of. Oxidation and reduction always occur together. You'll never have a reaction that there's only oxidation or a reaction that is only reduced. It's like it kind of makes sense. I mean, if something loses electrons, it has to go somewhere. If something gains electrons, it has to gain it from something, right? And so it's like yin and yang. I mean, it's always together. Oxidation, reduction. So one gets oxidized, and the other will be reduced. Okay. Now, what gets oxidized, all right, is what we call the reducing agent. Why do we call it a reducing agent? All right, it causes the reduction to take place. How does it cause a reduction to take place? Because it lost the electrons for something to get it. So it's the reducing agent. It causes the reduction. Okay, and so copper gets oxidized, and it's the reducing agent. It causes the reduction. While silver gets reduced, it's the oxidizing agent. All right, it causes the oxidation to take place. All right, because it wants electrons, it's going to take it away from something else. All right, so you could kind of look at it that way. All right. So the oxidation or oxidizing agent, all right, it causes the oxidation. It itself will undergo reduction. All right, it becomes more negative. So you notice here it started out with a plus sign, and then it became a neutral. That's not a negative, but became neutral. I was trying to underline the fact there was nothing there. All right, but it becomes neutral, right? So it becomes more negative. All right. And also another way that you kind of think about oxidation reduction, in time past, it talks about another definition of oxidation and reduction is the number of oxygens. Does it gain oxygens or loses oxygens? I know it doesn't apply to this situation here, but the oxidizing agent will end up losing oxygens. Okay. That's just another way we could think about it. Now, the reducing agent, it causes reduction to take place. So here's your reducing agent. It will undergo oxidation itself, and it becomes more positive. So here copper starts out with 0 and ends up with a +2. All right, so it becomes more positive, and oftentimes a reducing agent will gain more oxygen. So that's just another definition of oxidation itself. Now, as for reducing agents, you have like the alkali metals, so like lithium, sodium, rubidium, these guys, the alkali metals or the alkaline earth metals. All right, these are very powerful reducing agents. Okay, they themselves will be oxidized, but very, very powerful reducing agents, and that's because ionization energies are very, very low in itself. All right, and so they easily lose electrons. Okay, and so when you think about it this way, where you have and let me just give you an example. If you have like lithium, all right, and you have lithium react with water, what you're going to have is a lithium hydroxide plus H2. All right, and so what you see here, lithium typically has this case, lithium has no charge here, but lithium on this side has a +1 charge. So you can see that it itself has been oxidized, or it's a reducing agent. All right, it will reduce in this case here, right? It would get reduced, it would give off an electron, and really it reduces the hydrogen. So that's that's the big thing on that one. Okay, so very, very powerful reducing agents are alkaline earth metals. As for oxidizing agents, you have very reactive nonmetals. So like your halides, they're very, very powerful oxidizing agents. Okay, and so they're really good at taking electrons away from stuff, all right? So that way they themselves will be reduced. And that's just because they have very, very high electron affinities, okay? So one way for us to figure out the reduction, the redox reactions, we tend to look at oxidation number. Now, oxidation number basically indicates whether an atom or that particular substance, well, pretty much an atom, is neutral, electron rich, or electron poor. Okay, that's essentially what it is. All right, and so I'm going to go through, how we could determine oxidations to atoms. So, first rule, all right, if you have an atom that's at its elemental state, so for example, like sodium or H2, Br2, all right, you don't see any charges, any of that type of stuff. The oxidation number for these guys, all right, so the oxidation number are always 0, okay? So sometimes you see a solid, gas, it's liquid state, it's not bonded to anything, you don't see any charges, then we say the oxidation number is 0, okay? Now, what if you have a monatomic ion? Okay, so when it comes to monatomic ions and the oxidation number, all right, then the oxidation number is whatever that charge is. So for example, if you have like sodium ion, the Na plus, right, then the oxidation number is a +1. If we have Ca2 plus, the oxidation number for calcium 2 plus is a +2. If you have, let's say we're talking about chloride, right? The chloride ion, all right, its oxidation number is -1. If we have, for example, the oxide ion, which is 2 negative charge, then its oxidation number is just a -2. So if you have a monatomic ion, then the oxidation number is whatever the charge is. So now for covalent compounds and trying to determine the oxidation numbers, it's a little bit more complicated, okay? So, but I would say this, as for hydrogen typically its oxidation is going to be a +1. Oxygen, its oxidation typically will be a -2. All right, now everything else, because remember covalent compounds are two nonmetals or two or more nonmetals bonded together, it could get kind of really interesting, all right? But all in all, what you really want to kind of do, well, at least a pattern, what you want to kind of look at is that the most electronegative element is going to have a negative oxidation, okay? The least electronegative element within that compound is going to have a positive oxidation, okay? So what do I mean by that? So for example, let's look at this compound here, all right? SO2, right? You look at the periodic table and you realize oxygen is more electronegative than sulfur, okay? Now, what you need to also keep in mind is that this overall compound, all right, this overall compound has a neutral charge, all right? And so when you add up all the oxidations of each of the elements within this compound, it needs to equal 0, okay? And so, for example, oxygen, as I said, typically has an oxidation of -2. So this is -2, this is -2, all right? So in order for SO2 in this case to be neutral, the oxidation of sulfur is a +4, okay? So that's the way we kind of look at it. All right, let's look at another example. Let's say we were talking about NO, okay? Well, the element that's the most electronegative is going to have the negative oxidation. The one that's least electronegative is going to have the positive oxidation. So here oxygen is more electronegative, and typically it tends to have the oxidation of -2. All right. And so because it has the oxidation -2, for this compound to be neutral, then nitrogen needs to have the oxidation of a +2. Okay, and so that's the way you kind of want to look at it. Let's say if you're let's try a little bigger molecule in this case, right? So let's say that we're talking about HO and so this is HNO3, all right, nitric acid, all right, and we're trying to determine what's the oxidations for each of the atoms that makes up this compound here. Well, what we do know is that hydrogen is typically a +1, right? Oxygens are typically -2s, all right? And so now we got to figure out what's the oxidation of nitrogen, okay? Now remember, all of it together, when we add up all the oxidations, it must equal to 0. It has to, all right? And so we have a +1 here, right? Then we have these -2s here. So -2 plus -2 plus -2, that's -6, right? Plus a +1, so that's a -5. So in order for this to be completely neutral, then we know that nitrogen must be a +5. So this is the oxidation of nitrogen, okay? So how do we use this? Well, by determining the oxidations of each of your atoms, then you could easily figure out which atom has been oxidized, which atom has been reduced, what's the reducing agent, what's the oxidation oxidizing agent. I can never say that word correctly. Oxidizing agent. All right. And so let's look at an example. Okay. So let's look at this chemical reaction here. So we have two. Actually, I'm gonna do this in white. All right. So we have 2Fe2O3. So iron 3 oxide, solid iron 3 oxide, and it reacts with carbon gas, all right, and it's going to form iron solid plus carbon dioxide gas. Okay, and so this is a redox reaction, all right, but to prove that is a redox reaction, you need to find the oxidations for each of the for each of the compounds, each of the atoms here, okay? And so that's what we're going to do. And so let's go ahead and determine the oxidations, the oxidation number, all right? So I will start off with carbon because I think that's the easier one, right? This carbon here, it's in its elemental state, so the oxidation number is 0, okay? The iron, it's in its elemental state, so it has an oxidation of 0. Okay, so these two here. Now, if we're looking at this, so let's look at the Fe2O3, right? We already said that oxygen, in this case, when it's bonded to something, it will have the oxidation of -2, right? How many oxygens do we have? Well, we have 3 of them. So we got 3 -2 oxidations because there's 3 oxygens, right? Well, this compound is neutral, right? This overall compound is neutral. And so because the overall compound is neutral, this oxygen has a total charge of -6. So these 2 irons must have a total charge of a +6 in order for this to be neutral. So what is the oxidation of each of our irons? Well, if you do the math, you will notice that each of the irons must have a +3 oxidation in order for this to be a neutral compound. Okay, now let's go to the other side. Let's look at CO2. So we know that oxygen has an oxidation of -2, so -2, and there's 2 of them. Okay, so what must be the oxidation of carbon? Well, the oxidation of carbon must be a +4 in order for this to be a neutral compound. So now, let's kind of determine what has been oxidized, what has been reduced. Okay, so let's look at iron. Let's compare this iron to this iron. What's going on? Well, it starts off from a +3 to a 0. All right, and so in this case, we see that iron, the oxidation number of iron, goes from, all right, +3 to 0. So what does that mean? In this case, that means it gained electrons, all right, because the number became more negative. If it gained more electrons, it undergone a reduction, all right. Iron has been reduced. If iron has been reduced, and then this means that iron is the oxidizing agent. Okay. Now, if we look at oxygen, all right, hopefully you notice the oxidation of oxygen didn't change. All right, so oxygen didn't get reduced, it didn't get oxidized, so we don't have to worry about oxygen at all. But let's look at carbon. Carbon goes from a charge of 0 to an oxidation of 0 to an oxidation of a +4. All right, so it goes from 0 to +4. What does that mean? It means it lost electrons. All right, if it lost electrons, then it undergone oxidation. All right, if it undergone oxidation or has been oxidized, then that means this is the reducing agent. Okay, and so this is the way that we use oxidation numbers, and oxidation numbers will help us figure out what has been reduced, what has been oxidized in a redox chemical reaction.